Hello everyone, I'm Pragya Srivastav. I'm here to discuss about control system. The course code is KEC602. Previously we have discussed and finished till unit 4, and today in this lecture we are going to discuss unit 5, which is frequency domain analysis. In frequency domain analysis, specifically in today's lecture, I will be discussing more on Bode plot, the basic concepts of how we can draw a Bode plot, what are the steps to draw a Bode plot, and then using the Bode plot, how we can determine the gain margin and the phase margin of the Bode plot. So depending upon the gain margin and phase margin, they are nothing but the methods to define stability. So they are methods to define stability of the system. Let's say we are talking about any open loop system where G is such as the transfer function of open loop system. So we have to study the stability of the system. So Bode plot is the method, and then we will study Bode's stability criteria, like for what value of gain margin and for what value of phase margin the system will be stable or it won't be stable. Then we'll be seeing some numerical examples and advantages of Bode plot. Bode plot or Bode diagram consists of two plots. So we have to altogether draw magnitude plot and phase plot. In both the plots, x-axis represents angular frequencies, and whereas in the y-axis for magnitude we have linear scale, that is open loop transfer function in the magnitude plot, and in the phase angle of the open loop transfer function in the phase plot. Like let's say x-axis, this x-axis we have frequency in the logarithmic scale. So let's say this is sigma, and here we have logarithmic scale. Let's say we have 0.1, then another distribution will be 1, then another distribution will be 10, and then another distribution will be 100, and then it will be 10 raised to the power 3. So it is x-axis. Now in y-axis, so for y-axis, if we talk about magnitude plot, the y-axis is the magnitude or the gain of the transfer function. So we'll have this magnitude in decibels, and so this was magnitude in case of, this was gain in case of magnitude plot. Now when we consider about phase plot, this y-axis is the phase difference. So for phase plot, this is angles in degree, we can have 180 degree, 120 degree, 30 degree. So the reference will be minus 180 degree here. So magnitude of any transfer function can be realized as m will be equal to 20 log Gj omega Hj omega. What we have done, we have simply replaced Gs Hs as Gj omega Hj omega, since here we see that S is equals to sigma plus J omega. So this S is, this sigma is 0. So this is sigma plus J omega. So since sigma is 0, here we have, since sigma is 0, the property will be called as the variations with respect to. So here we see that when sigma is equals to 0, we can, wherever we have S, we can replace it by J omega. So we are writing Gj omega Hj omega, and here instead of sigma plus J omega, the variable across the y-axis is omega, not sigma. So how we can calculate the phase angle? Phase angle of open loop transfer function in degrees. So here the phase information about around the transfer function can be calculated for the frequency. Here we can see that the base or the logarithmic value is to the base 10. Now here we are going to study the basic concept. In this we are showing that how we can calculate the magnitude and phase of a system which is as simple as having just one pole at origin. In this system, we can say that the transfer function is 1 by s. So 1 by s is nothing but it's one pole at origin. So one pole at origin, we can write it as 1 by j omega, 1 upon 0 plus j omega. So magnitude plot will be magnitude of j omega at j omega. Here we can see that since it is 1 upon s, so 1 upon 0 plus j omega, the magnitude is 1 upon root over 0 square plus omega square. So magnitude is 1 upon omega. So 1 upon omega, now we have to calculate using this formula, magnitude. This term is 1 by omega. So we will do 20 log. So 20 log 1 by omega, it will be 20 log omega inverse or minus 20 log omega. So for different values of frequencies, for different values of omega, we can have a magnitude plot. Now coming on to different values, let's say we are taking omega equals to 0.1. When we will substitute omega equals to 0.1, so this 0.1, it will be 1 raised to the power minus 10. So minus 10 will make this minus 20 positive, and then we'll have plus 20 dBs. So what we can draw like this, we can draw here we have omega equals to 0.1, omega equals to 1, and omega equals to 10. So let's say for omega equals to 0.1, it is 20 dB. Let's say here we have 20 and here we have 40. So this is 1 point. For omega equals to 1, we have 0 dBs. For omega equals to 10, it is minus 20. So we are drawing like this, and this is the required magnitude plot. And we can say we call it a fall of minus 20 dB per decade. Why? Because we are falling 20 dBs. We are falling 20 dBs in 1 decade. So we call it minus 20 dB per decade. Let's say we consider a situation where we are rising like this. So this will be plus 20 dB per decade. So we have to see whether we are falling or we are rising. If we are falling, it is minus 20 dB. If we are rising, it is plus 20 dB. Coming on to the phase plot. Here we see in the phase plot we have, we have to have the basic, here is the magnitude plot only on the basis of the previous readings. They have also plotted the magnitude plot. Now coming on to, in this system we can have GSHS equals to K. So this is another concept where we don't have any pole, we don't have any zero, it is just GSHS equals to K. So M magnitude will be 20 log K, and here we don't have any phase information. In the previous example, we can see that the phase information can be calculated, because here also we can have the phase information like minus of tan inverse imaginary barrier. So imaginary here is omega and real here is 0. So we can calculate the phase from here also. Coming on to the phase information in this, here we don't have any phase information, so the phase will be always 0 degrees. Now coming on to magnitude plot, if K equals to 1, then magnitude is 20 dBs. If K is greater than 1, magnitude is positive. If K is less than 1, the magnitude will be negative, and it is very much evident from this curve. So depending upon these 3 observations, we are plotting this graph of 20 log K. So we can substitute the value of K, like K can be 10, 20, 100, 500, anything. And here phase plot remains at 0 for all the values of K. So here is the basic concept of 20 log, here is the basic concept of GSHS equals to K. Now we are now going to study a system where we have 1, 0 at origin, a system having 1, 0 at origin. In this we have M is equals to 20 log omega. So previously we had M is equals to 20 log 1 by omega. Here we can see it was 20 log 1 by omega. So now here we have 20 log omega. So 20 log omega, and this angular information will be always tan inverse. This can be written as 0 plus j omega. So tan inverse imaginary by real. So positive. This angle will be like this. So it will be always 90 degrees. So here we can have angle information as always 90 degree. Now, at point 1, the gain will be minus 20. At omega equals to 1, the gain is 20 degrees. At omega equals to 10, the gain is plus 20 degrees. So, just like we have seen here in this diagram, we were like in this diagram, we were falling like this. Let's say we were falling like this. So, it was minus 20 degrees per decade. But when it comes to 0, we will rise like this. So, it is plus 20 degree decade every time. So, it is at point 1, we have this. At 1, we will have this. So, this is point 1, 1 and 10. So, it is a fall of, a rise of plus 20 degree per decade. Now, coming on to example where we have a function like GSHS is equals to 1 plus S tau. Here the magnitude will be 20 log root over 1 square plus omega square tau square. And again the angle information will be phi equals to tan inverse real by imaginary. So it is 1 plus, it can be written like, S can be written as sigma plus j omega tau. Okay, so here from here only we can have this sigma. We can have, we know that sigma is 0. So wherever there is S, we have to replace it by simply j omega. So wherever we have S, we have to replace it by j omega. So it will be tan inverse, the real part is omega tau, and the imaginary part is, omega tau and the real part is 1. So here comes the phase information. So for different values of omega and tau, we have this plot. So let's say omega is less than 1 by tau, it will always remain for 0 degrees. The magnitude will be 0 degree. 0 degree when the omega is greater than 1 by tau, the magnitude will be 20 log omega tau dB and the phase will be plus 90 degrees. So this depends upon the value of omega and tau, whichever will be greater. Now, coming on to this another concept, the magnitude plot is having 0 dBs up to omega equals to 1 by tau radian per second. And from here we can say that omega is 1 by tau radian per second is having a slope of plus 20 dB per decade. So plus 20 dB per decade, in this case the phase plot is having an angle of 0 degrees up till 1 by tau, and after that it is plus 90 degree. So Bode plot is also called asymptotic plot, and we can also combine these two and make on the same scale. Sometimes you will see that let's draw the Bode plot using red. So we will be drawing it like this, and let's draw the magnitude plot using green. So it will be like this. So here we have minus 180 here, and here we have 0 dBs here, and it is the magnitude plot and it is the phase plot. So this is how we can overlap the two of them. So coming on to the concluding remarks. So whenever we have a constant k, the slope would be 0 and magnitude will be 20 log k, and the angular information will be 0. Let's say we have one pole at origin, 1 0 at origin. So whenever you have 0 at origin, it is always plus 20. Whenever we have n zeros at origin, it will be plus n into 20. Same will be with phase. If we have 1 0 at origin, it will give plus 90 dB plus 90 degrees phase angle. Whenever we have n zeros, it will be n into 90 degrees. Let's call about single pole. Single pole will offer minus 20 and n poles will offer minus into n times of 20. And coming on to the phase information, of course, minus 90 will be equivalent to 220 and then minus n into 90 will be equivalent to 270. So this is the conclusion behind the basic concept, and we will study more on this in my next lecture. Thank you.